Let's talk about another characteristic pattern for arrow pushing that is very common in reaction mechanisms. It's proton transfer. So proton is the same thing as a hydrogen, right? Now, in a proton transfer, the starting material can be protonated or it can be deprotonated. We look at both examples. Generally, for your proton transfer, the process generally takes place with two curved arrows or it can be one. It all depends on what you're given. Okay, so let's look at how we transfer a proton, or in this case, what we're specifically doing is protonating or ketone, right? So, as usual, you're going to look for your source and your sink. Your source in this reaction is your ketone. Your sink is your hydrogen, right? Hydrogens are always going to be sink because they only have one electron. Remember, your sink is that region that is low in electrons. Now, this is your hydronium ion, right? H3O plus. H3O plus, when we write mechanisms, we use H3O plus to represent our strong acids, right? So let's draw arrow from our source to our sink. So let's go from source. So remember, your tail of your arrow will start from a lone pair or from a bond, in this case from a lone pair, and we end at our sink. Remember, wherever the head of your arrow ends, it means you're forming either a bond or a lone pair. When you go from draw an arrow from a lone pair to an atom, you're making a bond, right? So we're making a bond between the oxygen and the hydrogen. Remember, all of this is still bonded to the oxygen, okay? And hydrogen cannot have two bonds, so we must break this one. So let's, based on the arrow that I've drawn, let's just draw what we would get, right? So you would end up with this. I have used up the lone pair, so I have a hydrogen. That hydrogen is still bonded to this, right? Hydrogen can have two bonds. All right, so we must break this bond right here. All right, and to break that bond, remember how we break a bond? We break a bond in essence by stealing. I like to say stealing. So what we have to do, right, is the oxygen is going to steal the two electrons that is being shared here and give it to itself. That's why I say we break a bond by stealing. Okay? So you have your hydrogen and your oxygen sharing these two electrons when it's in the bond, right? But hydrogen is going with this oxygen, so it needs to break away. To break away, it must break up with the oxygen, right? In breaking up with the oxygen takes everything with it. So remember, to break a bond, we're stealing. We're going to steal all the electrons that is in this bond and put it on the oxygen. That's what this arrow means, right? So let's draw the indication of these arrows on our product side, right? That's when you write the reaction mechanism. Your curved arrows have meaning, right? Whatever they mean must be depicted on the product side. So let's draw what is depicted from our first arrow. Always put back the things you never disturbed. I didn't disturb any of this. I didn't use this up, and I haven't done anything with the oxygen as it hasn't moved, right? So redraw that. So you redraw with your double bond O, put back your lone pairs, but I'm making a new bond. I'm using these two electrons to make a bond with the hydrogen. So these two electrons are no longer just on oxygen, they're being shared with the hydrogen. Let's make that new bond. That's my new bond. Okay. Now, I'm going to come back to the charge on this in a second. Let's look at the second arrow, what the second arrow is indicating. Hydrogen is gone. The oxygen and the hydrogen broke up. Yes. We break this bond by stealing the two electrons. So this arrow, and remember I told you this before, if you watch my other videos, when you have an arrow being drawn from a bond onto an atom, it means that the two electrons here is going onto the atom. Just think about what the arrow is doing. It's showing you the flow of electrons, the flow of electrons. So the two electrons here is flowing onto oxygen, or oxygen is stealing them. Okay, so let's draw what results from this arrow. I haven't done anything to this, and my oxygen is still here with the lone pair. I haven't used the lone pair. So let's put that, let's draw that. So I have my oxygen, put back the lone pair, this lone pair because I didn't use it. But look what we're doing. We're taking the two electrons in this bond and we're putting on the oxygen. So now I need to add two electrons, right? Now, question here is there a charge on this? Of course not. This is water. Water, the oxygen in water does not have a charge. It's neutral, right? And I told you, you need to remember when an oxygen is neutral. An oxygen is neutral when it has two single bonds and two lone pair. There's no charge here, okay? With that being said, let's look at this oxygen. I have one, two, three bonds and a lone pair. Okay, so this oxygen definitely have a charge. It doesn't look like this. It doesn't have two single bonds and two lone pairs. It has three single bonds, one lone pair. So this oxygen definitely has a charge. Let us talk about what charge is on this oxygen. Okay, now you can calculate it if you want, or you could reason it out. In mechanism, I suggest reasoning it out instead of calculating. It's going to take too long. So here you have a lone pair of electrons. They belong to oxygen. Oxygen and oxygen only, right? So electrons are negative. Oxygen has all the negativity right now, okay? When we make this bond, which is our nice blue bond over here, our lone pairs, these are now being shared between the oxygen and the hydrogen. So oxygen no longer has all the negativity to itself. It's now being shared with hydrogen. So if I have less negativity, right, on this oxygen, the charge here is going to be positive. That's how you reason that out. Same thing here, right? I have a positive charge on this oxygen, but I'm giving it negativity. I'm putting two electrons on it. So it cancels the positive charge out, right? Positive charge, but hey, here I come being negative. I cancel the positive charge. Oh, hence there's no charge on that. You can look at it that way. Let us look at an example where we deprotonate the starting material. So we have the same protonated ketone. We're gonna deprotonate it. Again, um, in this reaction, you look for your source and your sink. Okay, the source here is this oxygen, these lone pairs. Usually, you draw a bond, right, from the oxygen to the hydrogen. So you end up making, let's draw what is happening here. We end up with this. I didn't do anything to the lone pair. The lone pair is still there, right? Um, remember, when a lone pair, right? When you draw an arrow from a lone pair to a bond, you're making a bond with this hydrogen. So you end up with plus, rewrite H2O. I'm putting this back and these back because I didn't do it. I didn't use them up. I use this lone pair though to make a bond, new bond. I'm making my new bond red with this hydrogen, right? So I'm going to call this hydrogen A, hydrogen A. So now, right, I have water. I use the lone pairs here to make a bond with hydrogen A. So I end up with this, all right? We spoke about this before. Now I have three bonds on oxygen on a lone pair, right? So this oxygen has a charge and it is a positive charge. Remember, oxygen is neutral when it has two bonds and two lone pairs. Here I have three single bonds on a lone pair, which means that one of these lone pairs, I can show you from here. The lone pair here is being shared, right? It's being shared instead of just sitting on the oxygen, hence the positive charge. All right, let's talk about what's going on here. So this lone pair made a bond with the hydrogen, right? If I'm making a bond with this hydrogen, hydrogen can't have two bonds. So like I showed you before, you can't have this. Can't have two bonds, okay? So it means that the bond here must be broken. The bond here between the oxygen and the hydrogen must be broken. How do we break a bond? We steal the electrons. So you put the two electrons in the bond onto the oxygen. That shows that this arrow means electrons in this bond is going on to oxygen. They are no longer being shared with the hydrogen. That's why the hydrogen is gone. Nothing is being shared anymore, right? So the hydrogen leaves, the two electrons here go. So remember how you break a bond, you steal the electrons. Notice the electrons are, it's a flow. Take a hydrogen, must break the bond because hydrogen cannot have two bonds. So in this case, I didn't mess with this, put it back. I have my oxygen, right? I'm placing two electrons on here. So let's put the two new electrons on here. I'm going to put them in red. Now, this oxygen does not have a charge. You could look at it this way. You put the two electrons on here, that's negativity you're putting on the oxygen, but it has a positive charge already, I know. It's positive, and how dare us put two electrons here and cancel the positive. No charge is neutral. Okay, so, and if you want to think of, just always remember water, people. Oxygen in water has two lone pairs and two bonds, right? Your oxygen here has two lone pairs and two bonds, even if they're double. It doesn't matter, double, single. So this has no charge on it. Okay, so this is how you protonate and deprotonate. The fourth characteristic pattern is rearrangement, but I prefer to explain rearrangement when we look at reactions with alkenes where we generate the carbocation and we have an opportunity to rearrange. So